Hey team, you ready for our second example of Hess's law? So don't watch this one unless you watch the video on Hess's law, where we, explain the rules, Hess's law, constant heat summation, and then did a simple example, right? This is a more complicated one. So this one, I'm going to walk through it slowly. I usually move through it a lot faster on my own, do a lot of stuff in my head. But let's walk through. This looks pretty gnarly, doesn't it? Gnarly, good old 80s stuff, yeah. This has 4 provided equations, so this is a lot more challenging than the prior example, number 1, where we only had 2 provided equations. But it's the same concept. Ready? Oh, that's not example number 1. That's example number 2. We already did example number 1. So another application of Hess's law. This might take a little while. On the homework, you'll find various degrees of difficulty and length. Typical on my quizzes and exams, I like to use like maybe 3 provided equations. 2 is a little too easy. 4 takes a little while, so 3 seems to be a good number. Hint, hint. Lengthwise for exams. So it's challenging enough, but doesn't take that particularly long if you know what you're doing. Know how to play the game. So what is the delta H reaction, the enthalpy change or heat of reaction? And again, standard conditions, doesn't matter. It doesn't have to be a standard conditions. It just depends where you get those values. If you're not at standard conditions, those are probably going to be different. And here's the reaction of interest, right? So 2 moles of solid boron plus 3 moles of hydrogen gas, giving us 1 mole of the B2H6 gas. All right. So let's say we can't find that in a table anywhere and we can't run it in the lab. And we look around at some of the literature and we find 4 equations that we can manipulate in some way. So when we add them all together, we get that, right? This is the equation of interest. I'll box this. So the game says manipulate equations 1, 2, 3, and 4 in such a way so that when you add them together and cancel things out and simplify it, you get that. And then because if we manipulated them, we manipulate the values based on the rules. If we reverse it, we change the sign. If we multiply it by some factor n, we multiply delta H by the same factor because enthalpy changes are extensive properties. Extensive properties. And then these are additive. Delta H overall will just be delta H1 adjusted plus delta H2 adjusted plus the adjusted 3 plus the adjusted 4. Not that tough, really. So remember the thinking process. I'm going to start with the first species and see if I can find that in just one of these 4 provided equations. If it's in multiple ones, that makes it a little bit too challenging. And then once I've got that, then I'll take the second one, and then I'll take the third one, and then I'll, and if I got extra stuff, I might have to, cancel some things out. Let's walk through it. Let's look for boron solid. Do you see that in equation 1? Nope, I don't see boron solid. Oh, I see it in equation 2. You see that right there? So there's boron solid. It's not in equation 3 and not in equation 4, so that's great. All right, so I can play with equation 2. Now, the goal is to get how many moles of boron, 2, on what side? The left-hand side, the reactant side. This is what happened on the other one. Oh, isn't that nice? I already have 2 moles of boron solid on the left-hand side. Yay, I don't have to manipulate this. So this stays the same. So equation 2 stays the same. That gives me my 2 moles of boron. Check. On the left-hand side. Yay. Let's go to hydrogen gas. Do you see hydrogen gas anywhere? I see some. I don't see any hydrogen gas in equation 1. I don't see any hydrogen gas in equation 2. These look like different types of combustions, right? The first 3 look like all combustion reactions. I see hydrogen gas in equation 3 and not in equation 4. Yay, happiness is. So I see some hydrogen here. Let's do that in green. And some hydrogen there. So that's going to be equation 3, allows us to get the hydrogen. Okay, so let's take a look. We want hydrogen on the left-hand side. Everybody agree? Is hydrogen on the left-hand side? It is! If it was over here, I'd have to reverse it and multiply that by, change the sign, right? Or multiply by -1. Is the coefficient correct? I want a 3. But I only have a 1. So tell me how we remedy this. Hey, coach, multiply it by 3. Okay, let's multiply this by 3. All right, so we don't have to reverse it, but we have to multiply equation 3 by 3 in order to get the correct coefficient of hydrogen on the left-hand side. This is working. It looked pretty scary, but it's like a little dog barking that, doesn't bite. You're like, yeah, whatever. Well, let's move on to B2H6. Hopefully there's an equation that only one equation has this. Well, that one has B2H6. Equation 1 has B2H6. Equation 2 does not. It's all this B2O3 garbage. Do you see B2O3 in the overall equation we're interested in? No. So this is better cancel out, right? If you get this B2O3 solid floating around, something's wrong. I don't see B2H6 in equation 3, and I don't see B2H6 in equation 4. I see a bunch of water floating around, which isn't in the equation of interest, so the water needs to all cancel out. So it looks like, I'll do this in blue, the B2H6 is only in equation 1. Hey, this is working out pretty nice. We want the B2H6 on the right-hand side. Is it on the correct side? It's not. So I need to reverse equation 1. Now, how's the coefficient? What coefficient do we want? A coefficient of 1. It has a coefficient of 1. So all I need to do is reverse it. And I've got my B2H6 on the right-hand side. Hey, does something rub you wrong in the gut? We never used equation 4, did we? Things that make you go, why is that? This is a little more complicated than the other one. We cannot add equations 1 through 4 and get this, because the waters aren't going to cancel out. Right? Now, if we reverse this, the B2O3 will end up on the left. And there's 1 mole of it, right? So the B2O3 will cancel out. When I flip that, the B2O3s are going to cancel, aren't they? If I reverse this, I'm going to get 3 moles of vapor, water vapor on the left-hand side. I can't have water vapor in here, can I? So that's going to leave me with 3 moles of water vapor. Do you see the water vapor here? Ha 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 ha. See, I'm going to need, this is the extra difficulty level. You may not see it at the first, if you might just add these together and realize it doesn't work, and then you got to apply this. But you can see when I reverse this, that 3 moles of water gas is on the left-hand side. That needs to cancel that out. So if the water gas is on the right-hand side here, but it's on the left-hand side up there, I need to multiply this by 3 to cancel it out. Another way to look at it is the water, liquid water on there. If I multiply equation 3 by 3, I get 3 moles of liquid water on the right-hand side. So I need 3 moles of liquid water on the left-hand side to cancel out. So if I multiply equation 4 by 3, the 3 liquid waters will cancel the 3 liquid waters there after I multiply that by 3. And the 3 gas phase water will cancel out the 3 gas phase water after I reverse equation 1. Hey, and the B2O3, that'll end up here, cancel out. It's starting to feel better. I'm like totally out of room, dude. So what I want you to do is pause this. I'm going to pause this and rewrite equations 1, 2, 3, and 4. Okay, write the new equations. Reverse equation 1. Keep equation 2 exactly the same. Multiply equation 3 by 3. Avon, 2 or 3. And then multiply equation 4 by 3. Get all those new equations, which means we're going to change the sign on the enthalpy change for equation 1. That will stay the same for equation 2. We're going to multiply this by 3, the negative 286 by 3, and we're going to multiply the 44 kilojoules by 3. And then add all of the newly manipulated equations, add them all together, cancel out like species on either side, and we better end up with this equation. If we don't, we screwed up somewhere. If we do, yes! And if it checks, then just add the adjusted delta H values together. Bada bing, bada boom, we're done! All right, so go ahead and do that. Do it before I put this up. You'll learn better that way. Ooh, that took me a while. Holy moly. All right, so I left up the equation of interest that we're after, and these are the new adjusted equations. So remember, with equation 1, what did we do with equation 1? Right? We had to reverse that, right? So when we reversed it, we didn't have to multiply it by any coefficients, but we reversed it, so all the products became reactants, all the reactants became products. So I just flipped it. And so the new enthalpy change for reaction 1 will be the negative of the original. I didn't put the number in there. We can take care of that later. Gotten kind of squishy. Equation 2, we didn't change at all, right? So the new equation 2 is the same as the old equation 2. So I just rewrote it. And so the new enthalpy change is just equal to the old enthalpy change. I've effectively multiplied it by 1, right? Now remember equation 3, we had to multiply that by 3 to make the hydrogens work out. So that gives us the 3 hydrogens. Remember, for equation 1, we had to get the B2H6 on the right-hand side. Okay? Equation 2, we had to get the 2 borons on the left-hand side. Equation 3, we needed the 3 hydrogens on the left-hand side. So that's why we multiplied it by 3. So we got 3 hydrogens plus 3 halves oxygen, giving us the 3 liquid waters. That's the new manipulated equation. And since I multiplied by 3, I got to multiply the original delta H value by 3. So the new delta H3 at standard conditions is 3 times the old delta H naught 3. And equation 4, which was a little tricky, we needed that, even though it has nothing in the original equation, we needed it to cancel out some species. We needed it to cancel out the liquid water and the vapor of water. So we had the 3 liquid waters on the right. You can see we have now 3 liquid waters on the left. We have 3 water vapors on the left and 3 water vapors on the right. That's why we had to multiply equation 4 by 3 to cancel out all those waters, both in the liquid and gas phase. Well, if we multiply the equation by 3, we got to multiply the old delta H value by 3. So the new delta H4 at standard conditions is 3 times the original delta H4. Right, which was what, the 44 something. The numbers don't really matter. We'll just plug them in at the end. You can plug them in now and calculate those values and add them all together. You can do it later. I don't care. I don't care. So now, obviously, I need another board. I'm going to add that equation 1, the newly manipulated, plus equation 2, plus equation 3, plus equation 4, post-manipulation. And I'm going to get an overall equation, and I'm going to simplify it, and the simplified equation had better match the 2 boron solid plus 3 hydrogens, giving us B2H6 gas. And if it does match, then I'm just going to take that plus that plus that plus that. Hess's law of constant heat summation. Whoop, whoop. All right, so I'm going to add those all together and put it on the next board. This equation, this whole problem requires its own video. It's taken a while, right? But if you're on your own, you just fly through this stuff. Real quick before I do that, I just want to reiterate how you add these together. Take everything on the left-hand side of the arrows and add them all together. So I'm going to get the B2O3 solid plus the 3 water vapors plus 2 boron solid plus 3 halves oxygen gas plus 3 hydrogen gas plus 3 halves oxygen gas plus 3 liquid waters, all on the left-hand side, correct? And then on the right-hand side, we're going to get the B2H6 gas plus 3 O2 gas plus B2O3 solid, plus 3 liquid waters, plus 3 gas phase waters. That's your overall equation. Do that and simplify it for me. How's your overall equation looking? So again, you just added everything together. So you took the B2O3 solid, plus the 3 water vapor, plus the 2 boron solid. Now what I did is I took the 3 halves O2 gas and the 3 halves O2 gas from the 2 different equations, and that's just 3 plus 3 is 6 over 2, which is 3, right? So that really just sums up to 3 O2 gas. So I kind of simplified that there, right? You can combine those terms. Plus the 3 hydrogen gas plus the 3 liquid water. That's everything on the left-hand side. And then do everything on the right-hand side. You get the B2H6 gas, the 3 oxygen gas, the B2O3 solid, the 3 liquid waters, and the 3 gas phase waters. So let's take a look at what cancels. Let's do this in green. I see B2O3 solid, 1 mole on both sides. Bye-bye. That cancels out. That's a good thing. That wasn't in our original equation. I see 3 moles of water vapor on the left-hand side and 3 moles of water vapor on the right-hand side. Sayonara, you're gone. Yay. I see 2 moles of boron solid on the left-hand side. Oh, there's no boron solid on the right-hand side, so that stays. So that's going to come down here. Oh, somebody's knocking on my door. Hold on. Back in business. 4 kids at home in lockdowns. Yeah. They're everywhere. So anyway, we didn't cancel out the 2 boron solids, so I'm going to bring that down. So that stays. What else do we have? We got the 3 moles of oxygen gas on the left, 3 moles of oxygen gas on the right. The 2 3/2 add up to 3, so that cancels that. Yeah, this is simplified. Nice, isn't it? I see 3 moles of hydrogen gas on the left. I don't see any hydrogen gas on the right. So let's put the 3 moles of hydrogen gas on the left-hand side. So far, so good. I see 3 moles of liquid water on the left and 3 moles of liquid water on the right. So those cancel. Woo, it's really cleaning up. All right, what do we got left? That's everything on the reactant side. We've got a B2H6 on the right-hand side, but not on the left. So that's going to come down. And gone, 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 gone. And then you go, please, please, oh, past chemists of history, please Heisenberg, please Bohr, please Schrodinger, please let this work out. And then you look at the original equation and you realize that matches the original, my pens are stuck together, that matches the original equation, right? So you go match, yay, because if it didn't, just on a test, if that didn't match, just cry a little bit, skip it, and go on to the next problem. It'll take you forever to figure out where we pooped this one. So, hey, that confirms that our manipulation was correct. So now we know from Hess's law that delta H overall is just the sum of the and we happen to be at standard conditions here. And if you're not, it's not that big a deal. Number's just a number. So we're going to sum them. So this will be the new delta H1 plus the new delta H naught 2. Oh, there had to be 4, didn't there? Delta H naught 3 plus the new delta H naught 4. So I'm going to pause it. I want you to take those original values, manipulate them based on the fact of what we did with the equations, right? We reversed one kept the same, multiplied the other ones by 3. So do all that for me and see what you get. I'll write this up on the board and let's see if we match, my friends. Is that what you got? Please, please, please tell me so. Right. Everything is to the ones place, has an absolute uncertainty to plus or minus 1 kilojoule, so we don't have a non-rounded value in this case. So remember, equation 1 we reverse, so we got to put the negative sign in front of it. Equation 2 we kept the same, so we just leave it there. Right, the negative 1273. Equation 3 we multiplied by 3, so 3 times the negative 286 kilojoules. Equation 4 we also multiplied by 3 to get rid of all the waters, so 3 times 44 kilojoules. That was the only endothermic one of them all, which would make sense, right? Liquid to gas should be endothermic. Add them all together, so those negatives cancel out, so that becomes an endothermic or positive term. That stays as an exothermic or negative term. That stays as a negative or exothermic term, and that stays as a positive or endothermic term. So we've got 2 endothermic and 2 exothermic terms canceling each other. Not out completely. The overall process remains slightly endothermic, right, at 36 kilojoules. Wow, if you can do that one, you can do any Hess's law problem. I guarantee you. Woo! We're done with Hess's law. Yay!